Good morning, my name is Yahya Nazer, and I'm going to do this presentation for the next 90 minutes. We have divided the presentation into 3 segments, and at each segment we will stop and try to answer some of the question. If we didn't have enough time, I will post the answer to the question. You need to write, as it said, you need to send your questions to our facilitator. Basically, from my background, I'm a CTO and founder of Control Designer. That's a brand new startup company, but I worked for Dow Chemical for a number of years, and my last position was I was a fellow in Dow Chemical, one of the 6, and I was in charge of the process automation globally for the company. I'm currently a adjunct prof at McMaster University and co-chair of 106. Now let's talk about procedural automation. And what is the definition of procedural automation? It's a fixed step-by-step sequence of activities or course of action which define from beginning to the end what does a unit or what the process is going to do. ISA has been very active in this area. We have ISA 88, which refers to batch control, ISA 95, which talks about integration of enterprise control system, and ISA 106, procedural control for continuous processes. Therefore, and what was the scope of the work? I let you read it. This presentation becomes available, but we wanted to focus on continuous processes, not the batch processes. Therefore, the purpose was to develop standards, recommend practices, and technical reports on design and implementation of procedural automation. A standard committee, it consists of myself and Bill Ray, who is the other co-chairman. We have Charlie Green as our secretary and David Emerson as our editor, and we have a manager director is David Lee. Our past leader, Maurice Wilkins, was our managing director for a number of years, and Marty King was our co-chair before Bill joined us. We have a tremendous membership from different companies, manufacturers, and what we have done up to now is we have published our first technical report 2013. Then we are working on the second technical report, which is work process, and it's going to be sent for the 3rd bullet this month. And we have started to work on ISA 106 standard based on those technical report and more. Let's focus on technical report 1, which is models and terminology, to figure out where we want to talk about how to implement procedural automations. Therefore, as you can see here, these are the chapters and sub-chapters of the report. And basically, this is our word map of what are the words are inside the technical report 1. And you can see in some areas we have more pages. Therefore, this shows the page number, and this shows the number of pages for each of the sections. And basically, this report, you can say, talks a lot about the models and what are the models are. Therefore, we have 3 models: procedure requirement module, procedure implementation model, and physical model. Therefore, let's talk about them and see what they are. Let's talk about the physical model. Therefore, if you look at the map of Freeport from Google Map and dive into this plant that is being shown here. Therefore, at the high level, we have a plant module, and then we have a plant area module. Then we can divide the plant area model into unit module, and all of these definitions are provided in our technical report. And then we can subdivide each unit into equipment module. And once we have the equipment modules, then equipment modules are made of other equipment modules and or what we call control module. Control module is the smallest block that the module refer to, and These are block valve, for example, as a control module. The valve and equipment can be a pump with all of its associated I/O. We will talk about these much more in detail. Therefore, if you look at the layer of process automation, therefore, we have actual process is level 0. Then we have sensors and valves and temperature measurement, level measurements. That's our instrumentation, sensing of the process. Therefore, level 2 is where we have a process control, and it's divided into batch, continuous, discrete. ISA 88 looks after batch, ISA 106 looks after continuous control. And then if you go one level up, which is the MOM or MES, is basically manufacturing operating management. Therefore, and then when we go one up is business planning and logistics, sometimes referred to as ERP. Therefore, we are focusing on continuous control in these talks, and this hierarchical system is basically defined by ISA 95. But let's talk about batch. Why we need to have ISA 106 when we have ISA 88? In batch, basically what you can have is you can have recipe and you can use unit-based control with set of steps and transitions. You can make it more complex by having a same the same UBC but multiple product. Therefore, the recipe becomes very, very important, and we're generating lots of different products. We can go one more up, and basically we can have model 3, multiple product, multiple procedure. Therefore, each product have different steps and transitions, and then we need to have a batch manager to manage that. And then 4 is the pathway processing is different. What does that mean? Is a pump in one production belongs to A, and in another production belongs to B. Therefore, that's how normally a batch, a complex batch, is made of. Now, if we go forward and talk about difference between S88 and 106, a batch, basically the production cycle, if you look at it, in minutes and hours, we make something and we come back to washing and starting all over again. Sometimes we make more, sometimes we make less. And basically, the production cycle is in minutes or hours. It's very simple control strategies, pressure control, temperature control, and timing is critical, that when you start, when you're going to finish, and then batch manager commands equipment, not the module. Therefore, the pumps, the valves, all being under batch manager and the recipe control. And everything is recipe driven and is focused on cycle by cycle optimization. Whereas if you look at the continuous processes, normally the startup, running and shutting down is in days or years. Cracking furnaces can go up to 8 years or 10 years duration before next startup or next shutdown or next decoking. It's a very complex control strategy because abnormal situation, it's very critical that we don't shut the unit down because of abnormal situation. And a startup shutdown are critical. Doesn't happen too often, but you cannot train your operator when your furnaces comes down 8 years or 10 years. Therefore, you need to capture your operating discipline as a part of your unit procedure. Quality is critical. Unit commands equipment and control module, not the batch manager. And it's product wheel driven. Sometimes in your polyethylene plants, therefore you make one product and the other product, but steps and transitions are the same. Set points might change. And it's focused on quality of abnormal situation. Therefore, if you look at it, S88 has batch manager with UM is there, but it doesn't do that much. but the batch manager talks to EMs, talks to control modules, and talks to equipment modules. Whereas in SA106, the UM is basically driving force of talking to EM and CMs. Where are the targets for us? Is refining, petrochemical, polymer, and furnaces. And there's lots of benefits that we can show, and there's lots of paper published by Yokogawa and others and ABB and shows the benefit of implementing ISA 106, and I'm not going to cover those. But let's focus on some principles or requirements for ourselves. When we are writing a code, we need to repeatable, optimize startup, run, and shutdowns. Therefore, whatever we do this year to start a distillation 5 years down the road is the same procedure, same timing. We want to do abnormal situation management. If a feed composition changes or if the pressure goes up, we don't want the operator to come and take control. We want the system to take care of it. We want intelligent alarming based mode of operation. We want automatic enabling of equipment, devices, controller based on the mode of operation. Automatic swapping of pump, for example. Therefore, we want to enable the operator to run a process at the unit level instead of individual devices. And we want to do automatic sequencing of one plant. Therefore, this goes, the order is very critical, which one is the most important. Therefore, if you look at how we are going to operate a unit, basically the unit, we start it up, we run it, and we might have some abnormal situation. We run it again and we shut down. And this time is months, years. Therefore, if you look at it, I mean, the procedure to how to do this for every unit operation, for every distillation, every furnace exists. We cannot run chemical plant without these procedures. Therefore, if you go with the loop-based control, therefore the operators, when we are running here, needs to identify when to start, identify these states that we have, and then wait for the next steps and execute the command. Therefore, the operator is in charge. And if you look at this distillation column, for example, is very simplistic process control code. It has 14 block valves, 4 pumps, 8 control valves, 12 controllers, 0 override controllers, and basically if you look at it, the ratio of the controllers by valves is about 1.5, or dividing 12 by 8, because we seldom have a level controller to flow controller. Therefore, we have 2 of them working with 1 valve, and that's how this thing works. Therefore, the operator needs to worry about this, all of this, where it is and how everything works. And he or she might have multiple units to take care of. Therefore, multiple unit needs to be carried out. And there is a dilemma. In the old days, we have these controllers mounted on a board. They were very expensive. And therefore, when we were very limited, now we have very simple and very good instrumentation. We have a computer to write these controllers, but we still go back to the simplistic controller strategy instead of the one I'm proposing. Therefore, if you look at that, what is the operator needs to find out? He wants to find out the states that exist. Therefore, this tower needs to be in a maintenance wait. That means people can go in, open it, go inside the tower, check it, and come out. Then, because this is a vacuum tower, then we need to establish vacuum with this pad, dpad processes. We establish the vacuum, and once we establish the vacuum, then we need to go to process wait. What does that mean? Is this unit is waiting for its get the feed ready, therefore we can go forward. The first thing the operator does is establish bottom level. Oops, sorry. Problem. The first thing the operator needs to do is establish bottom level. Therefore, what does that means? That opening up this feed flow controllers and filling the tower to some level. Then we need to establish heat. Therefore, add the steam around the reboiler and boil the stuff up until we fill this drum, and then we set the reflux on, and then we fill these trays. And then we need to go to total reflux, therefore establish some sort of equilibrium, and then we go to run, and then we shut it down. Therefore, these are the states. Again, states are universal, therefore definition might be slightly different, but they exist for every. Now, if we go to another way of looking at this, which is the state-based control, or sometimes referred to as unit-based control, is the SPC identifies the state, SPC executes the command, and the operator permits predefined transition, and SPC observes for the next state. Therefore, it's similar to when we run the car with a stick shift, or we run it with automatic. Therefore, the automatic defines what gear we are in. Now, if you look at this distillation, this is the same distillation, but now it's implemented because we are going to use a state-based control or procedural control. It has more controllers. Why? It has 22 controllers instead of 12 that we had before. Base of 8, therefore we have 2.75 ratio of controller by I/O. And it would be good for you to go and check your process and see what is your ratio of controller versus number of controllers you have. Don't count the selectors. Number of PID controllers divide by number of control valves. Therefore, basically we have this complex control strategy, and let's just talk about this one. Therefore, what we have here is that we're taking the level, and remember, one of the things we want to do is to fill the tower. Therefore, we want to fill the tower up to here. Therefore, what we are going to do is this level signal comes to a level controller. A startup level controller goes to enable selectors and basically controls the valve. This flow controller is not active at this point. Therefore, this is the strategy that we have. Therefore, we have a LC startup controller, feed flow controller, enable selectors. The other one, what we have here is that we have two temperature controllers. This is very useful because sometimes to control this temperature, if this is our desire to control this temperature, it's very difficult to control it because the top temperature, it's to control the steam, you have lots of instability and problem. Therefore, what we do, we start with the lower temperature with this enable selector, and then we move up to this one once we establish a better procedure. Then we flow control, and then we control the valve. Now, we have number of controllers as override controllers for those abnormal situations that we talked about. We have a high pressure override. Therefore, if the pressure of the tower goes up, we cut the steam. We alarm, but we cut the steam. If the bottom temperature goes high, then we cut the steam. Therefore, we don't create some polymers there. If we have the bottom level goes too low, therefore now we are evaporating too much based on the temperature controllers, others. Therefore, your pumps are going to shut down. Therefore, we cut the steam. And then if the high level, the level at the top goes high, we are going to cut the steam. If we can see, I have 3 controllers here, go to low selectors. Then I have the result of that, and the high pressure goes to a low selector from the flow, and then we control the valve. And these are abnormal situation control strategy that I refer to them with yellow color. Now, if you look at that, if you look at the list of states or steps that we have here, and then looking at this controller strategy, the level controller needs to become enabled only, work only when we are doing established level, and then go away. The feed flow controller should work with the heat up, total reflux, and run. Total reflux, sometimes you don't need it, you need to cut it back, but let's just assume everything works. And then what we have here is that the temperature controllers that we're controlling the steam, it works all the way through heat up, total reflux, and run. And the selectors and then the flow controllers is basically the same thing. And if you look at all of these override controllers, they come in at heat, total reflux, run, because then there's no steam to control it. Therefore, we need to come up with this matrix, and you will see the example later on, that this matrix basically tells each individual CM or complex CM that whether they are enabled or not enabled. And the same thing applies for all of the alarms associated with this CM and complex CM. Now, therefore, how do we do this? How does this enablement work? We need to define different states or steps of a unit module. In this case, we have maintenance wait, vacuum, process wait, established level, heat up, and so on. Define transitions. Therefore, what we have here is we say, aha, from run we can go back to total reflux. From run, total reflux, we can go back to run. But from run, I cannot go to maintenance wait. From run, I can go to shutdown, but from run, I cannot go to established level. Therefore, there is a pattern that the pattern says we go straight down, but if something's happen, process wait, we can go to maintenance wait. From heat up, we can go to process wait. And therefore, from shutdown, we can only go to process wait and then go to maintenance wait. We will talk about this a little bit more. And the other thing is very important is that we need to identify that what is the transition. Therefore, in this case, when we have a step, the transitions is basically all of the common logics for all of our pumps and all of our block valves, all of our controllers that enable us to go from established level to heat up. What does that mean? The level should be greater than 30% and the pump should be ready. Therefore, if we have these two conditions, the system automatically should go established level to heat up. Therefore, we turning the feed on, we are filling the distillation, and when it reaches 30, and this is very simplistically for 1 or 2 minutes, therefore we don't get noise, then boom, and the pumps are ready, then we go automatically to heat up. And then each CM's enablement, we need to tell the each CM's, like this pump or like this block valve, at what step you are, because transition is instantaneous. In 1 second it happens, then it goes off. But we're going to tell this pump that when you are in heat or when you're in total reflux or when you're in run, you can be enabled. And then we have an additional condition that all of the instruments are okay. Therefore, the enablement of the CMs is divided in 2 parts. What steps and then what are the additional things are. Therefore, if you look at this, therefore that's a step. But then there is another way that we have situation when we have steps and then we have equipment module. Equipment module can have its own steps. Let's look at that. For example, this is a step structure for a tank or a distillation to a pump with a block valve. Therefore, and this is a step for a pump because that's different. Therefore, it says be in not ready and then go to become ready, then open the block valve, then start the pump, then go to the run and stop the pump and close the block valve. Therefore, as you can see, this is the same step structures that we had for the unit, but now this is the EM. Therefore, what we are going to do is we need to come up with something called mode of operation. And what we do is we say, what are the mode of operations for the pump? Not ready, ready, run, stop. Very simplistic. Therefore, this steps of the unit decide which one they want. Therefore, we have a one-to-one relationship between steps and mode of operation. And the mode of operation has a one-to-many relationship with the EM steps. And then we have feedback. Now, this way, if we change, for example, instead of having this step commanding this, if we put a dual pump here, everything is easy because it's the command of mode of operation changes, not the overall scheme of things in the process control or in the steps that we have. Therefore, what we're saying is plant module, area module, unit module, equipment module, control module, and basically control module have enablement. This represents steps and transition, mode of operation, and enablement. Let's just go through a very simple example. We have a tank, we have some physical tag names, we have steps, and this is the matrix to matrix transition. Therefore, we're saying that from maintenance weight we can go to process weight, and from process weight we can go back to maintenance weight. Therefore, this is a drawing here, and you can see we can have steps, manual transition, automatic transition, or manual automatic transition. And next is that now we can go from process weight, we can go to fill, manually we can go back and up, and here is a more complex one, that how we are going to go from maintenance weight, process weight, fill, heat, and run and shut down. The slides are available. If you have any questions, you can send a question now or ask me later. Therefore, let's just look at this, that how does these things work in realistic life. For example, as I talked about, is this steps. There we go from fill to heat, level needs to be above, pump needs to be ready. This is a logical way of writing it, and this is the actual code, or in a much more detail. Therefore, let's start this unit. We are in process weight, nothing is going on. We go to process weight and nothing is still going on. We go to fill, that means we are opening the level controller, flow controller, and filling the tank. Then we add the steam to the jacket and heat it up. Then we go to run, that means level control now, instead of level controlling the top flow, feed flow is controlling the bottom flow. And the pump is running, and then we shut it down. The distillation example is provided in your handout, and basically I'm not going to go through this complex one here for what we have talked about. Therefore, this section, we took us 27 minutes to get to this section. We talked about batch versus continuous, models, state and steps and transition, UMEM, and basically, therefore, I'm just stopping and looking at the questions, try to answer the questions you have sent.